Hello, class. I'm Jacqueline Blake, and this is my application of fuzzy concept for its fuzzy clustering and pattern recognition. I'm going to present an overview of the application. First, I will present a methodology for the application as taken from chapter 13 of our text, Fuzzy Sets and Fuzzy Logic. We will look at the fuzzy pattern recognition. I will present a human random keystrokes and biometric file methodology, and then I'll look at future applications of this presented methodology. I will then look at applications from literature, applications for human recognition based on biometrics of the iris, the air, and our voice. And the Sergino model, we'll look at the recognition based on biometrics for fingerprint and the Mamdani model. There'll be a conclusion and references will be presented. So a background to this. From chapter 13, we learned that cluster analysis explores the classification of objects into categories, and then pattern recognition is searching for structures in the data. So biometrics makes it possible to identify ourselves to digital systems, and through these systems, identify ourselves to others in cyberspace. The four primary methods of biometric authentication in widespread use today are facial recognition, voice recognition, fingerprint, and iris recognition. Other developing areas include recognition of one's ears. And in looking at them, the fingerprint and iris recognition are the most secure recognition types, whereas face and voice has the lower cost point. So a background to my proposed methodology. This is called the random keystrokes biometric. Fuzzy set theory in pattern recognition and cluster analysis was already recognized in the mid-1960s. And the literature dealing with fuzzy pattern recognition and fuzzy clustering is now quite extensive. That's from our Klir and Yuan text, and I found that to be very true. I was pleasantly surprised. So given the prompt from the text, chapter 13, fuzzy pattern recognition exercise 13.2, it said, write a computer program for the fuzzy C-means algorithm for different initial fuzzy pseudo partitions. And it gave an example how that is to be accomplished. And so by looking at that exercise, I thought about it, and I came up with this random keystrokes biometric. So the assumption I am making is that each character in a keystroke is in some way a significance indicator to the biometrics of that person. An approach to the methodology includes analysis by Python code for a randomly generated character file. And this file is just the subject randomly typing on the keyboard. And then I analyze also a biometric character file, which a biometric file will contain some important information pertaining to this individual. It could be some past passwords, could be the name of the person, just anything that is typed frequently on a keyboard that would represent some of the characters that are frequently punched. And then I looked at the CRIS to fuzzy association, the fuzzy equivalence relationship, a fuzzy membership function, and then the pseudo training that would need to be done. We explored the fuzzy application by looking at how it could be used for password decoding, application fit for biometric classification, application fit for dexterity, left versus right-handed inclined person. And this is just showing you how the methodology was developed. So this is the random keystroke distribution. After I passed it through the Python code, it just said, well, for the letter F, I typed 68, 69 character letters. And then each letter is broken down all the way down to letter S. It's typing done in 1.5 minutes. And of course it's timed. And this would be the first pass. Of course, to develop something, we would need quite a few passes of this, and it would include training the algorithm to recognize certain patterns. And then after the Python code was used, I then moved to Excel just to create the X sub I values for each. And so there are a total of 423 characters typed in the time interval of 1.5 minutes. And X sub I being assigned here is the fuzzy assignment for each cumulative count of the characters. And of course, this is going to add up to 1. So this was explored in Excel. I then moved to the biometric file. So this is the second input file. And I was quite amazed at how clearly this file, once I passed it through the Python code, established certain linguistic terms. And so in doing this, uppercase and lowercase characters are being treated as 2 different data points belonging to one group. So that's just saying an uppercase E is the same as a lowercase e. And then distinct crisp boundaries translate into fuzzy assigned linguistic terms. As you can see here, I have linguistic terms of high, medium, medium, low, and low. In addition, the characters that are not represented in this biometric file will be marked as NR. And so that gives me another fuzzy assignment of NR, which means it's not represented in the biometric file. And so from this, I created a membership function with the not represented being, would have been here. And then the low, medium, all the way up to high relations give a significance value, are used for significance value down here. So the fuzzy linguistics did translate into very nicely, as you saw, the high being EL, medium being the letters L, B, R, and D. And so analysis of each letter was important. For the most frequent letter keystroke from the first file passed was the letter F, which has the highest fuzzy relation of 0.158. So this letter is, however, linguistically low on the scale. And so it is used here, and it gives us a significance value of 0.016. The next character being the letter E, similarly is given a linguistic value of high, meaning that it's high in the biometric file, and so it's given a significance value of 0.1. So the goal is to collect several files of timed random keystrokes from a given subject at a particular point in time. And then the cumulatively each complete file of keystrokes would produce a pattern for identifying an individual and the relevance to their biometric file. And so this is the complete significance for the pseudo partition, which is what I set out to do from chapter 13.2, exercise 13.2. And so I achieved a final goal of 0.39. So that was the initial pass, and that can be developed, could be developed as we go along. But it's just showing how this pseudo partitions and fuzzy biometrics can be explored. So future applications of this fuzzy pattern methodology, I thought about how it could be used. Users do reuse passwords or portions of passwords to manage the mental strain of remembering multiple passwords on many applications. And by reusing passwords or portions of these passwords, each person has developed a pattern for typing certain characters. This pattern can be identified and used as a secondary means of authenticating a user's to prevent things like password lockout. So the I am not a robot authentication is something you've probably come across. This is where the computer asks us to click on street signs or pictures with cars in it, just to make sure that you're not a robot trying to access their system, right? So this could be used in that circumstance. And so password decoding and cybersecurity is another place that this could be explored. And the application fit for dexterity, trying to figure out if a person is left versus right-handed inclined. This is something that I would like to apply to figuring that out. Then there's a relationship between keystroke sequence and the timestamp of each keystroke and the interval information that could be further analyzed here. And then there's a sight impaired keystroke verification for those of us who are over 40. There's the concept of you get to 40 and your eyes just don't see as well as they should anymore. And I also considered neuroscience and Alzheimer's prediction. What if this could be used to predict some decline in your motor skills and possibly a link to Alzheimer's? This is just exploring ways that this could be used. So then I started to look at literature. How is pattern recognition used in a fuzzy way to identify biometrics? And I came across these two texts, hybrid intelligence systems and modular neural network of type 2 fuzzy systems. These books are by Professor Patricia Maylin. This one is Professor Maylin and Oscar Castillo. And so these are published. I also looked at Professor Lewis's Foundations of Fuzzy Control for looking at the methodologies behind fuzzy systems and the fuzzy multiple attribute decision-making text. And so Professor Maylin did outline some pattern recognition concepts, and the example of fuzzy system used for pattern recognition here are the eye, ear, and voice recognition. The human recognition is first parsed and goes through this fuzzy system to come out with one identification of a given person. Industry applications include also fingerprint pattern recognition. So this is the most popularly used pattern recognition, and it's good because our fingerprints are ridged, or they're covered with concentric rays patterns, which gives us 10 unique fingerprints. Each identical twin, even identical twins, have unique fingerprints. And we have 10 fingerprints as opposed to one voice, one face, and two eyes. And password, PIN codes, and smart cards can be lost or forgotten, but our fingerprints are not easily stolen or lost or damaged. So in looking at this model, the Sugino measure was used. The Sugino model is also known as the TSK fuzzy model. It was proposed by Takagi, Sugino, and Khan, and it's used to develop a systematic approach to generating fuzzy rules from a given input-output data set. It is a good model for fingerprint because it's good on nonlinear surfaces. So as you can see here, similar to face, the recognition pattern from the prior slide, there are 3 input here, and this is that the fingerprint image here is actually broken up into 3 images, and then each section is run through the Sugino model. So for facial recognition, there are some advantages. And so by looking at that, Professor Milin did point out that the face recognition has advantages over eye scan and fingerprint measures used in practice. Face recognition could be performed even without the subject's knowledge. And we see that that happens a lot these days. This is possible, whereas many biometrics require the subject's cooperation and awareness in order to perform an identification or verification, such as looking at an eye scanner or placing their hand on a fingerprint reader. The facial biometrics data used to perform the recognition task is in a format that is readable and understandable by a human. So for example, assuming that a person was incorrectly denied access to a site by an automatic recognition system, that decision could easily be corrected by a security guard that could pull up the image stored for that person's face and comparing the actual person's face with the image that is stored. Facial recognition is not generally associated with crime database, at least not as much as fingerprint recognition is. And so it's not as, it's probably easier to present to people. So the face is recognized as one entity when it's passed through the fuzzy inference system. It is the complete face is recognized without explicitly isolating different regions in the subject's face, as we saw before. The Sugino measure for the fingerprint is basically looking at different regions of the fingerprint. So with all of this presented, there is some core to pattern recognition. And the basics, the core to pattern recognition systems are the input, the weights, and the summation, and an adapter function. So the input values are multiplied by weights and added, and then there's also that a threshold amount, and a threshold is a point of departure or transition. So the basic structure of a fuzzy inference system consists of the 3 concepts: a rule base, a database, and a reasoning mechanism. The reasoning mechanism performs the inference procedure. And then I wanted also to look at ears as a human biometric. I found this interesting because our ears don't age as opposed to our face that ages. And so Professor Milin also presented this in the modular neural networks text. And so first the image is captured and then it's normalized. If it's a zoomed out image, it's created in a way that gives every ear a similar sizing. And then she looks at the image contrast. This air is then broken up into 3 sections, kind of like the fingerprint. And the models are passed through the inference system. So it's broken up into the shell, the helix, and the lobe, which are the inputs to each module of the network, with 3 submodules in each module, and 3 modules with a total of 9 submodules. The integrator is the fuzzy, the integrators here. These are the fuzzy inference system of type 1 fuzzy rules. In this case, Mamdani fuzzy logic reasoning with 3 input linguistic variables and 1 output linguistic variable with the 3 membership functions. So processing of each module, it's important to know the equation for recognition rate of each module is created, whereas the recognition rate for the first module, the second, and the third. And then there's an averaging of the recognition module to look at how it is performed. The integrator is a fuzzy inference system of type 1 fuzzy rules with Mamdani reasoning. I said before, this helix, shell, and lobe is whether it's a low, medium, or high match. And 2 tests are performed with different membership functions. In the first case, the triangular membership function. In the second case, the Gaussian. And the rates, the ranges are between 0 and 1. So very essential to any fuzzy inference system was the optimization methods. And I found this very interesting, that even after the modules are passed through, there's that fitness for total errors divided by the total test data. So there's a fitness gauge that is very important. So the optimization represents a convergence of the recognition error to 0. The method chosen to optimize this fuzzy integrator was a genetic algorithm. After applying the genetic algorithm, a better recognition rate was achieved. And so, as you can see there, the output was a better rate. Also key to a fuzzy inference system is creating a defuzzification method. We do have an input of fuzzy or traditional crisp data, and then we have output of a fuzzy set. But the defuzzification is important to extracting the numerical values. Defuzzification refers to a way a numeric value is extracted from a fuzzy set as a representative value, and it's very important to the end of coming up with results. There are some Mamdani fuzzy inference system defuzzification methods that were presented in the Hybrid Intelligent Systems book. There's a centroid model, the bisector, the MOM, which is the mean of maximum, as you can see here, and then the SOM and IO and largest of mediums, the smallest of maximum, and the largest of minimum values. So in conclusion, we can see that the biometrics make it possible to identify ourselves to digital systems. And through these systems, we identify ourselves to others in cyberspace. 2 classes of biometrics exist. They're the behavioral biometrics. They're generally used for verification, and that was the class within which my proposed random keystroke biometrics would fall. And then there are the physical biometrics. These can be used for either verification and identification. Of course, they're much more reliable. physical biometrics explored here were iris, fingerprinting, air, lobe, and facial recognition. So with development, a random keystroke fuzzy application can be used as a means of verification of a subject's identity. Research on biometrics application is ongoing. There are various fuzzy models are used, such as the Mamdani and the Sugino fuzzy models. Fuzzy inference systems are a good fit for identifying patterns in biometric data. And with that, I'm presenting some of my references here. And if there are any questions, please reach out to me at jblake3@binghamton.edu. It's been a pleasure meeting you all and learning from your presentations. Very good presentations have gone so far. Please stay connected. Thanks and have a great day.